Welcome to VTeach. Today we are going to discuss about instruction and instruction sequencing. So how a computer instruction will be represented. You can see here how the computer instruction will be represented. The computer instruction will be represented in two halves, opcode and address. So this is the representation of a basic computer instruction. And in this diagram we are having the memory which is going to represent the partitioned memory where instructions will be stored at one part and operands will be stored in another part. But while writing the instruction, we are going to use both the opcode and operands. So opcode is going to specify the operation to be performed on the operands. So address, in some books it is represented as operands. We may call it as operands also. So the opcode is going to specify the operation to be performed on the operand. Similarly, operands is going to show the values on which we are going to perform the operation. So that is the meaning of the computer instruction. So to know about this computer instruction, we have to learn about the resistor transfer language. So to learn the resistor transfer language, we have to know what is happening in the resistor and what is a resistor also. So the operations executed on data stored in resistors are called as micro operations. So what are the data that we are storing in the resistor? If I am performing some operation on those resistors, so such operations are called as micro operations, small operations. Say for example, if I am taking move R1 comma R2. So R1 and R2 are both are the resistors and I am performing a move operation here. So I am going to move the values from R2 to R1. So it is a simple operation. So such simple operations are called as micro operations. So on the resistors we are going to perform the micro operations. So representing these micro operations is nothing but resistor transfer language, representing such micro operations in terms of resistor transfer language. Say for example, I have written move R1 comma R2. So this is the instruction understood by the computer. But in resistor transfer language, I am representing the same instruction as R1 reverse arrow R1 plus R2. So representing the same instruction in resistor transfer language will be in this format. So we can see the clear difference in resistor transfer language. We are going to use resistors and on those resistors we are performing some operation. Those operations are called as micro operations and representing them in a user understandable format is called as resistor transfer language. So for representing the language we are using some symbolic notations are used to describe the micro operation. So here I have used a plus operator to represent the addition between the R1 and R2. So such things are going to be done in this resistor transfer language. So to know about the resistor transfer language, we have to see about a resistor. What is meant by a resistor? So a resistor will be always represented in the form of a rectangular box with the name represented in the center of the rectangular box in capital letters. You can see here it is represented in capital letter the name and it is represented in the center of the rectangular box. And remember, the resistors will always be represented in the form of a rectangular box. And here in this B diagram, the resistor individual bits are being shown here. So 0 is going to show the 0th bit position of that resistor, 7 is going to show the 7th bit position of this resistor. And in the C diagram, we can represent the number of bits at the top of the resistor. So by simply representing in this way, we can say the length of the resistor. So I can say this is the 16-bit length resistor. It is a 16-bit length resistor. A resistor can be represented in two halves, that is lower half and upper half. So I have taken in this example a 16-bit resistor. This is a 16-bit resistor and this 16-bit I am dividing into two halves, that is lower 8 bits and upper 8 bits. So lower 8 bits I am representing as PC of L. So here I have considered a program counter resistor, and for that program counter resistor the lower 8 bits are called as PC of L and the upper 8 bits are called as PC of H. So PC of H is going to represent the upper 8 bit values. So this is how the resistors are going to be represented. Now coming to the resistor transfer notation, what happens in resistor transfer notation? So remember, all the resistors should be represented with the capital letters. The resistor should be represented with the capital letters. The names of the resistors should be represented in the capital letters, and to perform any replacement operation, that is represented in this format. So I want to move from R1 to R2. Whatever the content that is present in R1, I have to move it into R2. So for that operation, I am going to represent a reverse arrow. Such symbolic notations are used in the resistor transfer notation. Similarly, for any conditional type, I am going to use a colon. So P colon R1 reverse arrow R2, which means this operation is going to be done whenever this P is going to be satisfied. So let us consider, if P is equal to 1, then only this operation is going to be considered. If otherwise P is equal to 0 means this operation will not be performed. So such conditional statements can also be written in resistor transfer language. So here I have represented very clearly how that is going to be represented. So some of the basic symbols and that are used in resistor transfer notation we are going to see now. So here, as we have said, the resistors are represented with letters and numbers. So we are representing the resistors with letters and numbers, and we are using parentheses for representing a part of a resistor. So for example, PC resistor is a 16-bit resistor. If I want to represent a lower half of this, then simply I am going to write PC of L. If I want to represent an upper half of this, PC of H, simply I am going to write. Or we may write a part of the PC from 0 to 7. We can simply write it. Or we may write the upper part also from 8 to 15 also we can write. So a part can be represented by using parentheses. Similarly, reverse arrow is used to denote the transfer of information, and comma is used for separating two operations. So if I am performing two operations at a time, then simply we can use a comma here, comma R3 reverse arrow R2. So simply we can separate the two operations with a comma. So these are the simple things that are present in the resistor transfer language. Coming to the CPU organization. So in the CPU organization, we are having three types of CPU organization: single accumulator organization, general register organization, and stack organization. So CPU organizations are divided into three types: single accumulator organization, general register organization, and stack organization. So the results are actually going to be stored in the accumulator. So such type of organization is going to be called as single accumulator organization. So the accumulator has to be saved to memory quite often. So the accumulator is having a very less amount of memory, or it is a resistor which is having very less number of bits. So we cannot store every time the results in the accumulator. So simply we are going to store the results whatever that are present in the accumulator into the memory, and again we are going to store another results in the accumulator. So in such type of organization, we are going to use the accumulator resistor very frequently. And coming to the general register organization, the resistors will hold whatever the operations that are going to be performed by the memory. Resistors will temporarily hold the data and going to perform the operation. And coming to the stack organization, the operands are simply stored in the stack and the results are going to be stored in the stack. So stack is nothing but it is a memory which is going to be organized in the form of last in first out, in the form of LIFO. So these are the different formats of the instructions. So these formats will be present in the three different organizations. So the different formats of the instructions are: 3 address instructions, 2 address instructions, 1 address instructions and 0 address instructions. So see how the instructions are declared in the 3 address instructions. As the name itself implies, we are having for the instruction opcode and 3 operands are represented here, R1, R2 and R3. And see how that is going to be represented in register transfer language. Similarly, for 2 address instructions, the instruction is going to be using 2 operands. R1 and R2 are the 2 operands, and we are having the representation in register transfer notation. And 1 address instruction, as the name itself implies, we are having only 1 address, and we are using accumulator as another operand. So that's why we are calling this one as single accumulator organization. And 0 address instruction, as the name itself implies, where the instruction we are not having any operands. So this type of instructions are used in stack organization. So coming to the types of instructions, the 3 address and 2 address will come under general purpose, general resistor organization. General resistor organization. The 1 address will come under single accumulator organization, and 0 address will come under stack organization. Okay student, we will see the remaining concept in the next session. Thank you.